In this tutorial, we're going to talk about how to use the substitution method for definite integrals. I know this is something that still confuses a lot of students, and I want everybody to be comfortable doing this for the rest of the quarter. We want to compute here the integral from 0 to 3 of x times the quantity 1 minus x squared dx. And most of you will see immediately that we need the substitution u equals 1 plus x squared. So the first thing you should write is the word let. Let u be 1 plus x squared. That tells the reader that you're choosing a new variable and you're calling it u. If you don't put the let there, it can be confusing that you're just somehow asserting that u is 1 plus x squared. Where did that come from? The let tells the reader that you're making that choice. Then compute the differential. Here du is 2x dx. Now, of course, we don't see a 2x dx, we see an x dx, so some people find it helpful to just write something like 1/2 du equals x dx, so we can perform the substitution more easily. Many of you can probably keep this in your head and do that all without writing this down, but it's useful to write that down until you're very comfortable with that. Then we can perform the substitution in this way. Here we have x dx. That's 1/2, as we already saw, du. Put the du over here. Then we have a 1 plus x squared here, and that's just u. Then we have the integral with the limits. Do we leave the limits the same, or do we change them? The answer is we have to change the limits if this equation is going to be correct. This 0 means x equals 0. And you know it's x equals 0 because we have the dx here telling us x is the variable of integration, so that 0 represents a value for x. Similarly, that 3 represents x equals 3. When we write down a new integral, we need values of u because we have the du here. So we ask the question, when x is 0, what is u? Of course, u here is 1 plus x squared, so when x is 0, u equals 1. And when I write that 1 there, that 1 is a value for u. Similarly, when x is 3, u is 1 plus 3 squared, which is 10. And now we can assert that this definite integral is equal to this definite integral, and we just evaluate this integral without going back to the variable x. How do we do that? We keep the 1/2, we anti-differentiate u squared over 2 from 1 to 10. We end up with 100, that's 10 squared, over 4, minus the 1 over 4, or 99 over 4, and that's the correct value for the integral. What if I had left the limits as 0 and 3? What would I get? Well, the integral from 0 to 3 of u du is actually u squared over 2 here from 0 to 3. We still have the 1/2, so end up with 9/4 minus 0, and this is wrong. Here's what I see a lot of people do. I see a lot of people try to write that the original integral is equal to this, which, as we know, is wrong. But then I see them evaluate this and write 1/2 times u squared over 2 from 0 to 3, and then rewrite that as 1/2 times the quantity 1 plus x squared over 2 from 0 to 3. Well, we already know that what this symbol means is 9/4, which is the wrong answer. What does this symbol mean? Well, if I plug in 3 here, I get 1 plus 3 squared. Oh, that should be a squared there. So I would get 10 squared, which is 100 over 4. And then I subtract plugging in 0, which would give me 1 over 4, and I get 99 over 4. Now that looks like the right answer. What's wrong with this? It's that this is wrong. This is 9/4. This symbol here, this expression here, is 99/4. So there's a mistake here. This is not the same as that. And of course, as we've already seen, this integral is different from this. So when you do this, you're actually making two separate mistakes. And it's wrong of me to take off 1 point when I see this. It should be 2 separate points taken off when something like this you do on an exam, because this is wrong and this to this is wrong. And you might ask, why is it not okay to make 2 separate mistakes if I come up with the right answer? In other words, what's wrong if there are a whole bunch of mistakes along the way? Imagine you've learned to do math by writing something like 19 plus 6 is equal to 22 minus 15, which is 25. Well, 25 is the right answer, but when you write this, it's like you're writing nonsense and just happen to get the right answer along the way. What you have to learn in a calculus class is how to do things correctly, how to write one expression accurately equals another, and then evaluate the thing you want to evaluate. You need to do math properly, not by writing that something is equal to something which is wrong, and then by some chance getting the right answer at the end. So it's very important that you learn to change the limits properly. And changing the limits properly is easy when you just ask yourself the question, when x is 0, what is u? When x is 3, what is u? And then you never go back to the original variable and you end up with the correct answer. We'll go through one more example of this. Let's say we want to evaluate this integral. This is similar to the one that was on the quiz for most people, but not exactly the same integral. In this case, most people would very nicely say let w be sine x. You can use any variable, u, v, w, whatever you want. Remember, we're going to write let here to indicate we're choosing w to be this new variable. dw will then be cosine x dx. Be sure you write it out clearly like that. Then this integral is just an integral sine cubed x, which is w cubed, cosine x dx. That's exactly what our dw is. And what are the new limits? Well, we have to ask ourselves, when x is 0, remember this means x equals 0, what is w? Well, w is sine x, so we have sine of 0, which is 0. So don't think I just left the limit alone. I changed from x equals 0 to w equals 0. Then we ask, when x is pi over 2, what is w? W is sine pi over 2, which is 1. So this definite integral has the same value of this definite integral, which is just equal to w to the 4th over 4, 0 to 1, which is easily seen to be 1/4. Remember, if you're writing this as an integral from 0 to pi over 2, w cubed dw, this is wrong. This has an answer. This integral is properly evaluated as w to the 4th over 4 from 0 to pi over 2, which is pi to the 4th over 16 all over 4. That's pi to the 4th over 64, which is totally wrong. So don't write that this integral is equal to this integral. And don't write that w to the 4th over 4 from 0 to pi over 2 is the same as sine to the 4th x over 4 from 0 to pi over 2. Remember, this expression means pi to the 4th over 64, whereas this expression means sine to the 4th of pi over 2, which is 1 over 4 minus 0, which is 1/4. They are not the same. Also, don't start throwing in indefinite integrals. In other words, do not write that this is equal to integral from, or just integral, w cubed dw, and leave out the limits entirely, and then somehow change back to sine, and then put the limits in. Because this is a definite integral, it's a number. This is a function of w, this is a function of w, and this is a number again. This is the correct number, this is 1/4, but it's incorrect along the way. It's okay to evaluate an indefinite integral first. If you're going to do that clearly and separately. Let me show you how you would want to do that. Just erasing all this stuff. If you want to use an indefinite integral, tell the reader that's what you're doing. Use words like first, find integral sine cubed x cosine x dx. Let w be sine x. dw is cosine x dx. This indefinite integral is now an integral of w cubed dw, which is w to the fourth over 4. Don't forget the plus c because it's an indefinite integral. Then we can write that this, let's finish this. We put w back, convert it back into x. This is sine to the fourth x over 4 plus c. We've evaluated the indefinite integral. Then we can evaluate the definite integral. Just by taking an antiderivative, which we now know, sine to the fourth x over 4. Remember, we can just take any antiderivative, so we can just ignore the c. In other words, think of it as 0. From 0 to pi over 2, and get the answer of 1/4. And we should separate that a little better. So you have two choices. Change the limits properly, or write very clearly that first you're finding the indefinite integral, then you're using that to find the definite integral.